notes.
My name is Peter Farrell, and I work with learningtech.org. We do everything from classroom courses to after-school programs to summer camps. Anything I'm missing here? Let's see, and it's all tech-related, as the name implies, and my background is a math teacher. So I might be one of the least techie of the learning tech people. But even the least techie person in learning tech, that's saying something. So I put up a video on YouTube and sent it to a math teacher or two, and it got around to somebody who knows somebody. And I want to thank you for having me here. I hope it's informative. That's my only hope. Hacking math class. Let's see. Like I said, I'm a math teacher. My background is in math, and the first time that I got to use a computer was in college. And it wasn't in the math department, it was in the business department. A business information technology, whatever teacher had us making programs in, recognize that one, basic, yeah. So that shows you how long ago that was. And according to my transcript, I took a class in Fortran, but I have no recollection of that whatsoever. So it couldn't have made that much of an impression on me. As a Peace Corps volunteer, the latest technology in my classroom in a community school in Kenya, Mount Kenya, was log tables. They had these in the back of their textbooks, yeah. And as I do now, I had to learn it right before I taught it. So log tables, and nobody all the way back to John Napier argued with using that technology. And nobody was arguing, let's do it by hand. We want to do long division. So it wasn't until years later, when I was a math tutor and I finally returned to teaching, that I wanted to give students the best tools possible for learning math. And this was the early 2000s, and graphing calculators were just being accepted in schools, but they weren't understood very well, and there was still a lot of pencil and paper stuff. But why use a graphing calculator like this? I think it's showing some kind of exponential function when the graphing software of the day was able to do it much more visually appealing, like e to the x, as everybody used Geogebra. You just graph something and want to snap a tangent onto it at any point. There's tangents. There's my tangents. Sometimes you want to find the slope of a tangent line. This is only for calculus. If you're not in calculus, you can't even approach such activities, but there you go. So I still have students who have the graphing calculators, and if you have a laptop, you've got a lot more available now. So let's see, where was I? I was in a school up the peninsula, a public high school, and I was coming from the business world, and so I was like the tech expert in the math department, because I knew how to use Word and Excel. And so the school, I introduced the school to not Geogebra. Before Geogebra, you paid for something called Geometer's Sketchpad. And they had it at the school, but they hadn't put it onto their computers yet. So I actually teamed up with the tech guy and physically installed the software, because none of the other teachers were up to it or were interested, or it was not in the curriculum or something. So in the old days, this was how you taught geometry, was using the compass and straight edge. But in the 21st century, you have these graphing tools which are available, where you can make perfect straight lines and perfect arcs and circles, and you can bisect angles and segments. Not available. You'll have to trust me on it. Right, this is the famous squaring a rectangle, thing. I could just do it on Geogebra, I suppose, but we want to get to the Python. All right, I hear you. So why would you, force people to use pencil and paper when there was, this new technology that was available that, could do the messy stuff? You wouldn't have to deal with dull pencils or those, the compasses that wouldn't stay at the right radius, and annoying. So I thought this was a step in the right direction. Then I came across Seymour Papert's book, Mindstorms, and that changed my life. Because Papert said that students that have trouble learning math and science just haven't had the experiences necessary to kind of understand that. And at the same place where I was teaching at the time, I was trying to teach the students about negative numbers. And coming from the Northeast, I used temperature. When it's 20 degrees out and it gets 5 degrees warmer. And it was in California here, and they said, what, you can have negative degrees? So this is an example of something that you have to have the experience of something before you can understand these abstract ideas. I've tutored young students, young kids, my son's age, and have them do algebra, do the distance, rate, time kind of things. And so they know the distance they're cool with, time, of course, but rates, they've never thought about how fast they're going. 30 miles an hour, 50 miles an hour, 100 miles an hour, it doesn't compute yet because they haven't, driven a car or gotten a ticket. So how fast do you think you were going? So this was a brilliant book because he made the assertion that these experiences could be gotten by just making turtles walk around the screen on a computer. And he made a pretty good, I guess this next video is not going to work either, but he made a pretty good case. Nope. He made a pretty good case that everything worth doing in math education can be done using a computer. So I was impressed. By that time, I was working at a special ed school where the parents just wanted their kids not to hate math. So I was allowed to experiment with this and have them do these logo programs. And you can see that you're using loops, you're using conditionals, you're using variables, just like just like a programmer would do. So at every school after that, they got the turtle geometry treatment. For many of them, it was the first time that they'd actually created something on the computer in math class. So, and to teach cold, hard logic in the old days, you used to do geometric proofs. And given this information, you go step by step, and you leave out a step, and the teacher has to say, well, no, I think you didn't prove this right. But with a computer program, that's a much better teacher of logic, because if you leave out a step, the program just doesn't work. Okay? It takes the teacher's kind of judgment out of it, and if the computer works or it doesn't, well, as we tell the students, it's doing what you told it to do. So around this time, I came across another brilliant book called Calculus by and for Young People by Don Cohen. And this tiny book is mind-blowing, just like Mindstorms. The math man taught me that you can use technology, low-tech and high-tech, in order to come at a math problem from more than one direction. And coming at it from 3 or 4 different directions, you'll really understand that topic. So he kind of exploded the myth that you need 11 years of school math in order to even approach these calculus ideas by showing his students' work, some of them as young as 7 years old, that were using infinite series and, pi and e and sines and cosines, but some of it was just done with cutting up index cards or using manipulatives, and sometimes you were on a computer. So low tech and high tech was kind of put together. Highly recommend that one. He made the case that what we consider hard math is really just easy math, but it's approached in the wrong way. All this kind of influenced me in my journey to Python. If we're not experiencing these ideas by creating them and making them move and controlling them, then we're really just sitting back and listening to the teacher or taking notes, just following the authority. The question is, how do you get students to have these experiences? How do you set this up? I heard some people talking about Scratch, and I have a 10-year-old who was studying molecules in 5th grade. And he's not the top math or science student at his school. He's an artsy kid, and he's just as likely to just be drawing with a pencil and paper or doing origami, folding paper up. But he learned about molecules, and he wanted to make it move around the screen, so it was just another tool for him. You know, this wasn't high-level programming or, you know, pre-calculus or anything like that, but he knew how to make a forever loop, and here's a conditional, and he made a variable, so he misspelled it, but he made a variable called temperature, and when the temperature goes up, the molecules move around more quickly. Let's look at it, the big board. So the temperature is 0, there's nothing happening, so as the temperature goes up, they actually move temperature steps. So as the temperature goes up, they're moving 9 steps at a time or 10 steps at a time. That's how he used that to make it go more quickly. When I came home from my walk, he said, oh, I just need help with my game. I need to get them to bounce off of each other. So it was just a matter of doing that. As I say, this is not, he's not in some gifted program or something. This was just another thing that he felt like, oh, I'd like to see them move around on a screen. He made one and duplicated it a bunch of times and just coded some loops. So let's see. So a homeschooler that I've tutored for years is a major computer, enthusiast, put it that way. And when I introduced him to Logo, he said, oh, it reminds me of Python. He had taken a Python class. And so he said, do you mind if I do all my projects in Python? What teacher is going to say, yeah, you know, do it in whatever language you want to do it in? But I actually don't know why. I said, yeah, sure. Crap, now I've got to learn Python. So I have him to thank for forcing me to learn Python. And I'm glad that he did. He wasn't kidding. He does his pencil and paper work, but you know, if he calls me or emails me, I know it's about, you know, I need to do that math, the computer project. And we've done everything from simple equations to, you know, Fibonacci numbers in the quadratic formula, and most recently the big formula for regression, a linear regression, a bunch of data points and find a line. Most people put it into the graphing calculator. Well, what does the graphing calculator do? So I made him do that. And yeah, he wouldn't sleep until he got it right. So I wanted to show, finally, he's getting to the Python. My other son is in 7th grade, and he's doing pre-calculus, pre-algebra. Oh, that's right. I have a. He's doing pre-algebra. Now, if you're solving equations and there's unknowns in it, that to me is algebra. I keep asking him, why do you say pre-algebra? It's algebra. So he's learning to move these things around and do hundreds of these every night. Sometimes it's different numbers. They even get really cruel and make it fractions and stuff. And so he's bogged down in the computation or finding common denominators or something. But I said to him, well, it's really just all the same. You've got some number times x plus something. is equal to another number times x plus something else. So here's the pencil and paper, back to Don Cohen. You can start off with pencil and paper and solve this for x by moving all the x's together and all the other numbers together, factor out the x, and then divide by a minus c. So you've just solved for x. Now you can create a Python program, only works in Python, where you define whatever equation with your a, b, c, and d coefficients. And what did we say? You return d minus b over a minus c. That was it, right? D minus b over a minus c. That's right. So this should work. What were the other previous ones? Not doing that one. 2x plus 8, 5x minus 12. All right, so if we run this, then it was actually no, see if we get a good 1, 5, as long as they're not parallel. Okay. So even if you're working with the fractions, oh yeah. So 2/3, 8/9, a quarter, and 5/7. You'll probably need to put some floats in there or something, but yeah. So that's how you learn about floats and transferring, moving back and forward between integers. And I just thought this was an important thing for my son to be able to do, at least to check his homework, is because they're all of the same form, no matter if it's decimals or fractions or whole numbers or negatives, and you can use the exact same thing no matter what your what the coefficients are. I know I had my Raspberry Pi and was over at a friend's house showing him and his son's a freshman in high school, showing him Python. And so when I said, well, it doesn't matter what you have, let's see, return x squared minus x minus 1 or some such. So when you run this, then all you have to do, of course you're asked things like, what's the f of -5, and you're supposed to put that into the equation and do the number crunching, but this does it immediately. And this kid said, what website is that? I'm going to download that right now. Before we left that night, yeah, he was already playing around with Python. You have to just be able to see how it makes some of the drudgery a little easier, and hopefully I'll show in a little bit that I'm not trying to allow kids to get out of doing their arithmetic. It's more being able to think on a higher level.
So when we studied that, yes, the intuition was less, the drudgery was more. Pencil and paper, proofs and everything. At which part in the math education is drudgery required in your, I mean, we did the proofs and we did the calculations, we did the fractions by ourselves. You're saying, think more in terms of the intuition. I mean, get the big picture, don't worry about the numbers and the division, long division, everything.
Yeah.
Let the computer do it for you. Is there any facet of the math that you would prefer drudgery, the step-by-step by hand instead of the computer?
Sometimes you can't appreciate how great this stuff is until you've done it the hard way.
Okay.
I agree with that. And I definitely want my kids to be able to know what 60% of something is around, or but we all know if we get if we're faced with some division problem with 3 digits or something, you know you're reaching for a calculator. Okay, and Yeah, and the calculator's on everybody's phone. And even in Kenya, I mentioned I was in Kenya. We were just in Kenya over the summer, and everybody's got a cell phone now. So forget logarithms. So now everybody has got the capability of doing the arithmetic very quickly. Okay, but I still tutor students, and I'll whip out the calculator or the computer, and they're like, oh, no, no, my teacher wants me to do it by hand. And we'll see, okay, a simple fraction problem, maybe doing it by hand is not so bad, but we'll see some roots problems that, why would you make another human being do this by hand? So that's what I'm getting to. If this is our function, let's see. Everybody who hasn't had calculus yet, close your eyes. You're not allowed to see such a thing until 12th grade. So if this is, how to find f prime at a certain value. This is our function. So how to find f prime of x. I should make it a much uglier function, but f prime. So a derivative is really just the slope of a line at a point, a linear approximation, I should say. What am I worried about getting corrected for? I've got a math degree. So they used to call the run delta x, but now it's just h. And if we make it really small, well, I should show this, because we've got, here's the textbook version of it. And it really is just the rise over the run. This is the derivative of a function. So we'll put that into our Python program. This is the run. The rise is f of x plus the run minus f of x. And the slope, as always, the rise over the run. I could have done this and just return the slope. So there's really nothing calculus-y about this. It's just, I mean, if you've done slopes of lines, it's really no different than that. So this should give us our, so what's f prime at -5, I wonder? Ah.
Negative point.
I do here. Let's see. Ah, that's what it was. I was doing logo, so Python's exponentials. Pretty close to -10.9. How could we get it closer? Just make the run even smaller. I think it's about -11. Okay. Again, there's really nothing, that you need calculus to understand about that. Let's see. There was also a gentleman way back when. Okay. He came up with the idea of the calculus, I'm sorry, and this is called Newton's method. I work with enough pre-calculus students that need to find roots of functions. And something like this, you make a guess. This would be your first guess. And you find f of that first guess and also f prime of that first guess. And let's see, the slope is what, this side over this side? So that means that this side is the, let's see, this side divided by the slope. That was what he said. And you get x1, which is the next guess. You do that again, and you get even closer to the root. So in most cases, this works out pretty well. Let's see if I have a case where it doesn't. So I just want to define Newton, showing my East Coast origins here, Newton. Let's see. We'll repeat it 5 times. And this is going to do, let's see, the next guess is going to be the first guess minus f of the guess divided by f prime of the guess. And then we'll print all our guesses. So we only need the last one. We want to see how quickly it gets us to, let's see. But we need a first guess. So what I did beforehand was I created a graphing function for the good old turtles. You see at the top there, you import the turtle module. And this is a great leap from Logo. The creator of Python must have been enough of a fan where every release of Python has had a turtle module. And not the visual module or something that we have to go out and get, but that's already in there. So the turtle is going to walk around and make a graph of our function. Let's see, make sure that we've got our... Oh, we'll make it this function. So if the teacher says you can't use a graphing calculator, well, what if I programmed it myself? Can't I use that? So this was a much uglier function than the quadratic that we used, and there's 1, 2, 3, 4, 5 roots. And it looks like, no, that one's not going to be -1. I don't think they're going to be rational. But the students that I tutor that are taking pre-calculus, they have to narrow down all the possibilities, and they take the coefficient of this and the constant and divide and take all the positives and negatives of all the possible factors of, it does narrow it down from infinity, but you still could have to test 20 or 30 possibilities. So Newton, of course, is much easier to do. Is this, okay, I've got Newton here. So this helps us. This one is going to be close to -2. So if our first guess okay, I'll just did it 10 times. So we started at 2, and it got closer and closer to, that's the 0.789. Positive 0.7. Okay, so that's 0.789. Let's see. -2.5 maybe? Alt P. There we go. So that root is -2.44 around. And I mean it got here in five guesses. And then you can find the other ones using better guesses. -1. It's -1.1. Okay. So, yeah.
So your exercise that you're going through, it reminds a lot of what we're going through in our work lives. When we come from we're software designer or hardware designers, we create something known as a test bench. The test bench checks the actual work we're doing. And this graphing thing is to help us check what we're doing manually actually works out.
Yeah.
And so you're asking us to spend time, you're asking the student to spend some time, work with the libraries and stuff to create a testing environment so that when he does the rigorous calculation, he knows where he is.
Actually, with this one, since I think I made this one on Geogebra just to get something that had like 5 roots. So this one, I don't know how you would do this by hand. This one has no rational roots. So that's why I think that Newton's method would be a preferable, well, not only a preferable method, I'm not sure how you would do it otherwise. That's what your calculator is doing, and it's what your computer graphing software would be doing anyway, is using Newton's method. So the quicker that we get students to understand what's going on in here, and it's not just the magic box that tells me the answer, I think this is taking it into their own hands. How does the calculator do, well, the linear regression that I talked about? You know, in fact, even the textbook that I was using gave very specific instructions on how to put that into your graphing calculator. Okay.
The HP, by the HP model.
Yeah, that is one. Yeah, right. I'm a Casio guy. Sorry, it's only in TI. Yes.
Well, I think that like on the previous one where it did have rational roots, and you could have done it with this, and it would have gotten out these nice rational roots.
Mm-hmm.
There's such a value of seeing it in different ways. I took a kinematics class where we did it by hand, and then we did it in a simulator, and then we actually saw the robot move, and with a piece of graph paper behind it to see if it showed up in the same place. And you could always tell which of you thinks was wrong, because two of them would agree. And it gives you such a value to be able to say, I see the graph, I can see the roots are here, I can do it by hand, and if one of them's not right, I can kind of fix it up again until it is right, and not spend all of my days playing this game of something is wrong someplace, figure it out by going through all the steps.
No, you're right. With the Newton part, that's unrelated to the graphing routine that I use. So this is just seeing it in two different ways right now, but it's
Right, and if you could do it, if this were a quadratic you could do by hand, then you would also see three different ways of the same problem.
Yep.
And that adds a strange understanding to it.
Yeah.
In addition to the learners learning the Python and studying the Python, are these points of mathematics study as well? You can just look and think about these functions, these terms, and the entities they're manipulating. Do you have them spend that time?
If I can address that one of my favorite classes in the university was numerical methods, which is exactly that. I love numerical methods. It was like, how in the world can you do a sign? Like, write some big table inside? Yeah. Called numerical methods. Really cool. Sorry.
Yeah, no.
And at grade level that you're addressing the same sort of thing?
I think numerical methods kind of in a college level. Yeah. Yeah. But
same thing, just more detail. Like,
yeah.
Just stop it at a different previous in this lesson.
Yeah, that's right. But at a certain level, I mean, at a certain grade, they stop using y is equal to something, and they all of a sudden start using f of x is equal to something. It confuses, well, the kids I see, you know, a lot, because y changed from y to f of x, but if you're using Python, okay, it's a really important thing to be able to think in terms of functions, and a function is a really useful tool. Like, it really doesn't do it justice. You know, it's so vital to be able to call something a function and then call it later on in another routine.
Is it too early for the grade levels you focus on to drill down, why does this work? And what is it doing to be able to work?
Right.
Is it too early in the grade level to explore such questions?
How does it work?
Right.
How does it generate the numbers and plots?
For the graph, here's the xy position. It's just calculating its position. Here, it's really long. It's like 10 lines. Put your pen up, set your color to black. The step size is going to be 1/100th of a unit. Set your position to way over at -3, and then whatever the function of -3 is. Then put your pen down. Yeah, I've forgotten that a few times. I've got the big streak across the screen. Oh. Set your heading to 0. In the turtle module, that's okay to the right. And then 500 times, you want to just go forward to the right just a tiny bit, and then set your y value to the function of your new x coordinate. So it's really doing a zigzag. If it were a bigger step size, you could see that it's kind of zigzagging around the screen. If you make it a small enough step size, it's slower, but it looks like a nice curve. I think the fact that it's still called a turtle module and not something really scary, techie, mathy sounding makes it more accessible to, I was going to say kids, but God, you know, grown-ups who, I don't know how many scary haircuts I've had when the person says, well, what do you do for a living? I'm a math teacher. Oh, you know, they're having a conniption while I'm sitting there. Put the scissors down. We're doing real math, techie stuff. So I've gotten up to Python. We've been doing, you know, stuff with the pre-calculus or Algebra 2, and I've had enough experience with like homeschoolers or kids who are higher or lower in grade that you just find out where they can fit in, what they can do. Okay, you were showing Scratch. I mean, Scratch is golden. It's written in Logo. Derivatives are just slopes. If you've been doing slopes, you can do derivatives. So let's see. So I was thinking to myself, okay, great, we've got Python. What's something that I can experience, some real thing? I'm a mathy guy, and oh wow, look at that graph. And even my wife is like, oh, enough with the graph. Is there something real that, you know, in science class, at one of the schools I was math/science teacher, and how about science and physics? What can we do using computers that we couldn't do any other way? One of the things that I've thought of for years was the orbit of planets. It really looks to me like the sun starts over there and moves over there. That's just me. Okay, but these astronomers say that we're orbiting this, and you know, Copernicus said it was circles, and you know, Kepler said it was ellipses, and Newton came up with a formula that closed the door and shut off the lights, and there's no more debate about it. But really, does that really make, you know, elliptical orbits? So I thought about that for years. I tried to do it in Logo, and maybe I wasn't good enough, or Logo didn't have vector, you know, capabilities. I know it's got lists, but I didn't master the lists in it. I always went back to thinking about that. But it would be great to know, hey, all I did was code in this force and this velocity, and here's what I got. You know, there's no getting around, you know, learning that. How do you know that? Well, that's because I just did it. You know, there was nothing else on the outside. Even me showing it, yeah, it could be messing with you. I didn't show you the real, you know. For a student to do it is major. So somehow I stumbled across Visual Python, and that opened the door. Because I'm a math guy, I know my vectors, and in Visual Python everything is vectors. The position, the velocity, the force. All right, only those three things. But those three things are really important in these models. So the program does all the number crunching for you. Again, this is not something that really could be done by hand. And somebody saw the video and was like, oh yeah, that's Euler's method, where you know that you don't know the position of something, but you know where it's going to be facing. So you put it there and you face it and you make it go forward a little bit. Now you recalculate. I could do that a couple of times, but you know, your hand's going to get tired. So what better way than with a computer to do this? So at first I just thought of a projectile problem, just a simple, let's see. And no better way to start a program. Visual, visual. Because I was trying to import the visual or get the Visual Python on my Linux computer, and I was having all kinds of trouble. I'm not the best Linux, you know, the most experienced Linux guy. And the guy who created Visual Python was very active in the forums, and have you tried this and tried that? So I quite agree that, you know, this is the kind of community I want to be in. And that's the thing, we're talking as, you know, parents and people who are interested in math, but I'd love to get in front of the, you know, group of teachers like this and say, here's what you can do, and I'm available to, walk you through it, if you're going to do this with students, because we work with 100 students, this year that I've been teaching through the Summit schools, 2 in San Jose and 2 in Redwood City, okay? But if I could get a bunch of teachers, then it could be affecting a lot more students. And that's the only reason why this isn't better known, is because they just don't know about this stuff. I didn't know about this stuff before. Yeah, the kids say, can I do my homework in Python? I didn't know. So let's see. For the projectile, what I love about Visual Python, because previously, in order to do any kind of graphics, you had to do pages and pages of C++, and it was ugly. I wouldn't. I'm sure it made me. I was shocked from learning all the languages like C++ when I just didn't know why I was doing half the stuff. But with this one, if you wait long enough, I guess, you'll get a nice sphere.
Need to move that VPython window.
Need to move it? There you
Yeah,
go.
right.
Just move it. Great. And it's interactive, in theory.
It's straight, you can tell.
Yeah.
Glitching a little bit, huh? Close down all my Python. No problem.
Well, it's starting back up. Have you ever experimented with PyPy to start these programs?
No.
PyPy makes things like that go really fast, but it doesn't work in all cases, so I was curious if you ever had a chance. It's a really way of taking a visual thing like that. Like
Okay.
I saw this video editing, it was like clip, clip, clip. I was like, you can see this guy's being done now.
It's
Okay.
Something you might come up with things.
Thank you.
What's it called?
PyPy.
PYPY.
Yeah, I think that's right, technically.
That's the just-in-time
Nope, still gonna be-
compilation.
This is
Just
just
the-
that.
this
the whole
sub-process?
thing is on the
If
page
you move it, it
right
blocks it.
Ah.
If you move it, it blocks it.
there.
Let's see, how about
It's
just
it's a refresh problem.
VPython?
But, so it starts up and you have to
Move the window.
Move the window
Move the
in order to
screen,
make
yeah.
it go.
Mhm.
Yeah.
All right.
And it provides a light source? The hanging provides a light source?
All right, let's see. So we'll make our ball a sphere. And here's where we give it a, this would just be a projectile. So its position is a vector. We'll put it at 0, 100 meters up. And otherwise it defaults to 0, 0. Radius is 3. What's your favorite color?
Red.
Red. That was red, and most important thing for us visual people, make the trail, make it leave a trail.
Capital T, I think.
Capital true?
I think it's,
Capital T for true.
you sure?
Yeah.
In Python, yeah, but
Yeah.
if I'm wrong, I'll beg forgiveness. Okay,
Yeah, move that VPython window. Oh.
okay. Pi, you say, huh?
Right now, it takes a while to set up an experiment.
Yeah, we set up
VPython.
next.
So VPython is a whole another Python implementation.
It's
Oh,
a big
yeah.
library.
Okay.
So you
All right,
have
so
to
there's
move the
a-
window to make it, no, there it is.
There it is.
There it is, yeah. So we have it, it's 100 meters up. You haven't got it doing anything yet, but, right, we can zoom in and zoom out on it. Okay. Working. And we'll give it a velocity. This is going to be a vector. In the x direction, let's see. Nothing in the x direction, we're just going to make it drop. Actually, no initial velocity. Why don't we just, and then the force of gravity to be a vector, of course. Nothing in the x direction, and then negative 9.8 y direction. Nothing in the z direction. We'll do this 50 times or so. Let's see, we'll make the ball's velocity has to update itself according to the gravity, right? And then the ball's position updates itself, and here's the shorthand for that, according to the velocity. All right. Let's see. We'll say if it crashes into the, no, let's see. We'll just keep it going.
Yeah, collision detection.
If the y value is less than or equal to 0, just break.
Can we make it not red after all because it's against a black background?
Sure.
By yellow.
Yellow, that's a good choice.
Good solve. Okay, that was fast. So what I'm showing you, right, the bare bones, make a sphere, get this to do this, and we can tweak it however we want, because we want to be able to see what it does. So found out that making the rate in the turtle module at speed, but that'll slow it down. So it gets to the bottom and stops. If, let's see, we wanted it to bounce.
Negative. Subtract.
Subtract what?
Go back up and see if you hit the top.
Change the velocity.
Right.
Plus minus.
Plus minus.
Ball dot plus minus ball B.
Make the velocity.
Y. Yeah, just Y.
Put to the right. -1 times ball velocity.
Then the top. You need to check the top. If you hit the ceiling.
No, I don't think it's going back up to the ceiling. We can figure that out by, let's see, giving it a little bit of x direction here.
Okay.
Then what kind of, we're going to see. Oh yeah, then it just goes to the negative of that. Let's see. If we want to show this, let's see, we'll make the ball.
Is it moving in the z-axis?
The
Oh, just Y, just Y, yes.
Yep.
Just Y. Yeah.
Mhm.
Okay.
Oh, that's odd.
That's I thought it'd go back up.
So let's see, I think what it is the step size is too big. So if we, just like before, if we make the step size even just 0.1, then the force of gravity has to be changed, and let's see, then it's moving.
In position, you also need to multiply velocity.
Yeah, just use the dt, multiply velocity and
Mhm.
and ground don't mess with.
That's right, well, yeah, the force of gravity is already multiplied by that, right? Okay. We make it go a little faster and a little, repeat it a little bit more. Okay, so we have a projectile and we have force of gravity. Okay, now a student who codes that for themselves and sees that is, when you talk about Galileo, when you talk about, acceleration, you're going to have the experience to understand that. It might be like, what, Galileo never did this? It would have been so simple for him to just show like I'm doing. So, I don't.
It could be misleading because it doesn't conserve energy, right? So there is numerical dissipation.
And these are the kinds of things that you can absolutely code in. Elastic bounces or damping. Okay, so obviously not everything's going to bounce like that. So you can obviously change the display. I guess the scene.
Once the students have this, they immediately want to make a Madden football game?
Why not?
Well, I think a lot of times they'll start making a game.
Yeah,
Yeah.
some game.
Like, can you pick it so that it always hits this spot where they bounce?
Yeah, sure.
So they go off and they have fun for a while with their new shiny math toy. That's okay.
Probably with more realistic physics.
Height is 600. You just make it bigger.
What grade level is experiencing this, Peter, in your school?
Let's see. I haven't done the visual with the high school classes yet, but I've done this with he's a junior or senior, the homeschooler that I work with. So the display, you can make it larger, and as you can, it's got a little title on the top there, projectile motion. So you came here tonight to see the orbits, though, which we can use from this. You can just change this around to be a projectile. Let's see. So it's not going to be a ball, but let's see. We'll make the Earth a sphere. Making it on the x-axis. Let's see. -200, and the radius is still 3. Color. Actually, this is pretty cool. With Earth, only Visual Python does this. Let's see, material. And I may have left out an S there. Okay. That's the Earth. Suppose you want a sun. We'll leave that in the middle, so we don't need to say what its position is, but we'll give it a big radius. And its color. When it's big enough, we'll be able to see it. So let's see. Now let's see, Earth. Earth's velocity, we'll give that a vector in the y direction. Actually, call this t to 0. And of course, for the force of gravity, according to Newton, the force of gravity is just the magnitude of the, let's see, unit radial vector. So we need one of them. And that's just going to be the position of the sun minus the position of the Earth. That's the radial vector. Let's see. Unit has to be divided by the distance. So I guess we have to. So the distance, square root of, let me see, it is the Earth. Since the sun is at the center, this is easy. Earth's x coordinate squared plus the Earth's y coordinate squared plus the Earth z coordinate squared. Suppose the computer will want to know what a square root is. No. So force of gravity is just what? That little tiny number times the mass of the sun times the mass of the Earth divided by the distance squared. And that whole thing is multiplied by the unit radial vector. Times, let's see, and that's going to be going towards the sun. So let's see, all of these are constants. G, big M, and little m are just constants. And I did code in, went on Wikipedia and found out all the masses and the radii and all that, but it doesn't work out very, very well. So we're just going to come up with a number for those. Let's see. And all of this has to go inside the loop. The force of gravity. Earth's velocity has to be updated by the force of gravity in the Earth's position by the Earth's velocity.
We're becoming differential equations now?
Actually, I like to think of this as avoiding differential equations. Yeah, you're using vectors. There are ugly, ugly differential equations that if you want to find out where it is at t is equal to a certain time, okay, feel free. But with these vectors, which really is Euler's method, right? You go a little bit, turn, go a little bit, turn. Okay, that is what you're doing, is solving differential equations. We can print out t and find out where it's going to be, stop at t is such and so. Yeah, we can do that. If the Earth, no, if the distance is less than or equal to the sun's radius, then stop. Go back. Less than Earth. Yep. Okay. I feel like one of the Summit students. Oh, Mr. Farrell. Oh, did I leave something in?
You don't have to break right there.
Okay. Oh yeah, no, I want to save this as the get Python. Oh. Ah, I knew I left out an S. Materials? Because that's the cool part. It's not just a green sphere. So you can, oh yeah, it only,
Inconvenient when that happens.
let's see. Where is it? It's here somewhere.
Well, it may be on escape velocity, actually.
We just need to,
If you set the velocity a little lower, we can crash it into the sun instead. Piece of software. That would really good.
get around the whole.
So here's what's happening. Here's an orbit. So when you set it,
All right, good old ellipse, just like Kepler said. Let's see. Oh, here it comes. Still. It's leaving a trail of pollution behind it.
Just like the real Earth.
There, it's still going. So yeah, I was impressed at the Earth has got the material of the actual Earth there. Where are you?
It's an
Oh,
actual
nice, nice. It's the real Earth.
Wave,
Oh, it's the Middle East.
Google Earth in real time. It should be, huh?
Can I see my house?
It's on
Getting the source
fire.
of the light from the left.
Bouncing off the moon.
And that's a good point. I haven't even scratched the surface of what visual Python can do as far as changing the perspective and changing the light source and stuff like that. It's just so rich and I mean, this didn't take a whole lot of, coding. Actually, when my wife saw the video, she said, that is a lot of code. No, really not. In order to get students to play around with ideas in physics and astronomy or gravity, even history. Yeah, what was the big problem? Why was Galileo put in, house arrest? I mean, these kind of things have some bearing on, education, and I like getting the historical perspective of it, and I like getting the math perspective, the science perspective, and you're using Python. What could be better? I mean, if all this stuff, like you were saying, well, what if they just say we want to play with this? Play. Go ahead and play. Get used to using variables and loops and conditionals, and okay, you're going to come out of it with a pretty good grasp of computer programming. Okay, so that's my one trick tonight. I thank you for listening to my story leading up to this, but I'm honored to come in and share with you guys. I'd love to share with teachers and other parents and techies, and I do appreciate the context or the how about this, how about that. That would be, I'm writing that down, and I'll claim it as my own idea in my next. Then I was thinking, why not put in a light source? So if you have any questions, I hope I could answer them. Yeah.
Have you been approached by the Khan Academy yet?
No.
Have you heard of them?
Oh, sure.
Okay.
Yep. I love Vi Hart's videos. So people ask me why I don't put any narration on the videos. First of all, it's to make the students actually watch the video. My voice puts them to sleep, or maybe it's just grown-ups, or narration just for nobody in general. They tune out and they talk to their buddies. But also, yeah, Vi Hart is about the only person on YouTube worth listening to. Otherwise, you get the idea.
But you really could flip the classroom, the science classroom with this stuff. Have the kids do these experiments and work at home. And then when they come to class, the science teacher can say, well, left out.
Right.
Forgot gravity or something.
And where is the Earth at when time is equal to this many, days or something? You're right. It is approximating, Euler's method. And somebody was talking about the Runge-Kutta method to improve it or something. I'm all ears. But I think this was a way of kind of getting around it using the vectors.
For short time span. So that if you want to simulate millennia, you will lose energy very quickly with your.
It's like this balance in Paul.
Yeah, exactly.
Well, I think that one of the
So there are specific numerical methods for n-body problems, and especially for orbits, which are kind of conserve energy by construction.
This is called explicit method, the implicit method.
Yeah.
Which method?
This is Taylor method is explicit method.
Explicit.
There are implicit numerical methods that are more precise.
Okay, where you're actually telling it where to be at a certain
Actually,
time.
make some prediction where the velocity is, and then it calculates this velocity effectively as a for correction.
Like
So
with
it can Euler use current state to calculate next one.
Right.
And then implicit it can be reversed. It can calculate what would be, where would I be if I knew my final state.
Okay.
So it can be slightly reversed, but it's more precise.
Okay.
Yeah. Well, I think actually, if you go back to one of, I'm going to go back to your first roots problem with something like integer roots. It's true. If you come back and you say, look, we can tell this is exactly 6. Or you can look at the graph and say, well, it looks like it's about 6. Or you can run the numerical method and say, well, it's between 5.9999 and 6.0001. And you can sort of appreciate when you might want the exact method that's more precise. And when you just want a quick numeric value. And that you really do come up with, I mean, one of the big things that kids have with math is when they suddenly realize that no matter which way they do it, unless they make a mistake, they'll come back to the same answer, even if they didn't do it the same way as the teacher or the neighbor.
Can you put the file back up?
Sure. That's even what they ask in the class. See the code again?
How did you discover Visual Python? When did you start using it?
Let's see, I think it was only about a year or so ago. And it was probably just through searching on Google and searching on YouTube and seeing that people were doing cool things, and then seeing how easy it was to just, make a sphere and make it move using vectors. That was perfect. So it seemed like it wasn't a whole lot of work to me.
Were you looking for a tool, or you were just looking?
Yeah, I was looking for a tool to kind of visualize this 3D stuff. And I have done a 2D version on the Raspberry Pi, since Visual Python doesn't work on Raspberry Pi yet. Maybe someday. And using the exact same kind of idea, but just in two. Actually, I had to define a. No, they do have Vector 2D in the turtle module. But your turtles are just little spheres. They're little circles. Yep.
Have you tried the IPython notebook, especially the web-based IPython notebook? That's kind of getting really big in the scientific community.
Get my pencil out here.
IPython notebook?
IPy notebook?
IPython notebook.
IPython, okay.
Yes.
The IPython notebook and pandas are really, really popular,
Yeah.
and they visualize a lot of this stuff. And if you haven't seen the tool, I think you're really excited to hear about it.
And if you want to try, you can just get a free account on Bakari.io. That's a continuum analytics kind of website, and you have basically Python on your web browser, and the IPython notebook is part of it. So,
On a web browser. Okay.
yeah. Bakari.io.
Bakari?
Yeah. W-A-K-A-R-I. It's a continuum analytics project.
Right. So the short version is IPython is Python with some variations of making it a little easier to play with the command line. With the notebook option, it's a little like the notebooks over in MATLAB, where you can put down and you can say, oh, and here's my text, and it's in a nice markdown language, so I can highlight things and put in graphics. And then, by the way, I run this code and I get this graphic, so you can see what's happening and you can see the code behind it.
Okay.
In some areas, for example, oddly in computational biology, a lot of journals are just like, you have to give us the IPython file because so many times people make mistakes, as well as there are people who are saying, I do something kind of like it, let me plug my weird idea into your simulation and see how it works, because you had to publish the notebook. So that's an odd place where it's taking over.
We're getting a little short on time, but these questions are great, and we also have a little bit of time afterwards where we'll actually just play walking around and asking questions.
Okay.
So if we have a couple more questions real quick? No?
Yeah.
Well, I just want to make an observation, because for a room full of Python programmers, it might not be obvious, but just for kids to understand that a vector isn't just an arrow, but it actually is a tuple. I mean, that's something that they don't get. So educationally, this stuff is just amazing.
Right. And this is why to use it. I guess I just year after year of tutoring students, and they're saying, why are we using this? Or even worse, they're just trying to get that grade. And I'm asking myself, why is the teacher making them do it this way? When okay, not going totally over onto the computer, but they're not giving them any context of how vectors are used, but it's just like adding up arrows, really. Is that all it is? But, all right, I'll give it.
Real quick, let's just do some announcements. We will definitely have time for questions afterwards, and if you don't mind, maybe start protecting something.